Hey AP Chem, welcome to chapter 15. So now that we've talked through what acids and bases are, now we get to apply them to all the different situations that acids and bases have an impact on. So that's what this chapter is about. It's about the application of acids and bases in certain circumstances. So we're actually going to start this section off by talking about something that we touched briefly on in chapter 14. And it's what happens to equilibria if you have the same ion from two different sources. So this is called having a common ion. So for example, here's our situation. We have a solution of HF and NaF together. So in our beaker, when they made this solution, they put in some HF from one source, and then they also put in some NaF from another source. Okay, so what they're going to ask us at the bottom, they're either going to ask us for pH, which remember, basically that's a measurement of our hydrogen ion concentration, or they're going to ask us for a specific ion. Okay, so depending on what we want to know about is how we're going to set up the reaction. If we want to know about the hydrogen ion, we might set up a reaction that includes the hydrogen ion, but not the sodium ion. If we want to know about the sodium ion, we might set up a reaction that includes the sodium ion, but not the hydrogen ion. So depending on what you're looking at is going to be how you decide what you put into your solution. So before we get there, let's first just talk generally about this solution and consider what's present. If we have HF from one source and NaF, what do these things do once they hit the water? What's actually going to be there? This would be a good time to pause your video already and see if you can come up with a set of ions or molecules that you can say, okay, after this hits equilibrium, these things are definitely present. Okay, so looking at HF, HF is going to be a weak acid, right? So weak acids don't dissociate to a great extent. HF is going to be the majority of what's present. Will we have H plus? Sure, we might have a tiny bit, maybe like 1 molecule out of 1,000 molecules will dissociate to give us H plus, but we'll have 999 HF molecules to 1 H plus molecule. So are we going to have these ions to a great extent? No. The majority of what we're going to have is HF. Now let's look at NaF. This is going to be a soluble salt, right? So a soluble salt is going to break apart into ions like Na plus and F minus. The majority of what's going to be present is going to be our ions. We will not have much of our ionic compound left. So really, the majority species that are present are going to be these three: HF, Na plus, and F minus. Okay, so now that we kind of understand what's going on in our solution, here I'll write them over here. The majority of what we have are these three things. Okay, now let's look at a couple different things they could ask us to do. So first of all, they could ask us to calculate pH. So if we're going to calculate pH, the thing we really care about is H plus. So we need to write an equation that's going to end up resulting in us being able to calculate an amount of H plus. So if I use NaF, right, NaF dissociating is not going to give me any H plus. So that's not what I want to start with. What I want to start with is my other compound. HF dissociating or reacting with water is going to give us an H plus or a hydronium concentration. Remember, you can write this as the dissociation reaction We can pretend that it's actually a dissociation reaction, or we can write it as the actual reaction that happens. It does not affect our K value because water is a liquid and we can ignore it, right? Okay, so that would be an equation where once we get to equilibrium amounts, we have an H plus ion concentration here that we can now use to calculate pH. Now, they haven't yet given us a scenario, right? So let's just talk reactions for now. What reaction would we set up to find these different things? So to find the hydrogen concentration, the hydrogen ion concentration, we would use that reaction in purple. Okay, now what if we didn't want to know the hydrogen concentration? What if we wanted to calculate the sodium concentration instead? Well, this reaction, as we've written it, doesn't give us that information. So we need a different reaction that will result in us having information about the sodium ion. And that would be this equation. Notice in the end, if I can get an equilibrium position here, it will give me information about my sodium ion, right? Okay, now the most common mistake here, if you are told that you are given a solution of HF and NaF, and you're asked to find specific ions in there. The most common thing for students to do is set up an equation where these two react together, right? But as you look at this, again, you have to pause and consider the context, right? Will these two things actually react together? So we have an acid. Acids will react with water. Acids will react with bases. Acids might react with things like metals, but are acids going to react with ionic compounds? Probably not. Same thing with ionic compounds. Ionic compounds will dissolve in the presence of water, right? They could be involved in double replacement reactions. Could this be a double replacement reaction where your anions switch and your cations switch, right? Nope. Because if you switch your anions, you're going to end up with the exact same compound. So this isn't going to be a double replacement reaction. It's not going to be a single replacement reaction because that doesn't happen between two compounds. Let's think about our other reactions. Synthesis, no, they're not going to combine to form something bigger. Decomposition, no, because we have two things, not one thing. And combustion, no. So if you kind of run through the list of possible reactions that would happen, they don't fit any of them. And so what's happening is you have a solution where they're both dissociating inside that solution and then floating around together. They're not reacting together. Okay, so a general rule of thumb moving forward is you only combine an acid with something if it's a base or water. Otherwise, the context, they'll probably have to tell you what's going on. A metal gets dropped into acid and starts to react. Okay, now you have a single replacement reaction moving forward, and you can go write that reaction, right? But an acid and a salt are probably not going to react together. Okay, so now that we have this understanding of our solution, let's look at a specific example here at the bottom. Which solution will be more acidic? 1 molar HF by itself or 1 molar HF with 1 molar NaF? Okay, so let's set up these two examples and calculate down to the pH, right? To the H plus concentration, because it's that H plus concentration that's going to tell us if something is acidic or basic. Okay, so I'm going to delete my board. This would be a good time to pause and see if you can set up the two reactions, reaction 1 and reaction 2, and then fill in that ice chart. What's your initial amount? What's your change? What's your equilibrium? Okay, in this scenario, okay, I'm going to run out of space. So let me try this again. I'm just going to use the dissociation reaction for the sake of space. Okay, this is a weak acid, so I'm going to have X as my change. Now, I'm going to have the same thing on this side. Remember, I just care about my hydrogen concentration. And so I don't need to involve NaF in my reaction unless it's convenient. Remember, I don't really care about Na plus. I do have F minus in here, but I don't really need information about Na plus unless they're asking me about it. They're not asking me about it. They're asking me about a hydrogen concentration. Okay, now in this one, I still have initial amount of Na of HF. I don't have a source of H plus, but I do have a source of F minus, right? So we need to figure out how much F minus I have here from NaF. Now, eventually you'll be able to do this inside your head, but you may be able to do it inside your head right now. I want to show you, I'm going to write out that reaction of just to show you what happens with this and how I get that initial concentration. Okay, so if I have NaF and it dissociates like it will do in water, right? It's a soluble salt. And I have an initial amount. Now it's a soluble salt. What's my change going to be? Do I know how much it's going to change, or do I not know how much it's going to change? It's a soluble salt, right? So it's going to dissociate completely. That's the definition of a soluble salt. So I'm going to dissociate all of my NaF. That means if I start with 1 molar NaF, I'm going to get 1 molar of my Na plus ion and 1 molar of my F minus ion. So 0, 1, and 1. Molecularly, that's like saying if I start with NaF and I dissociate that, I get 1 mole or 1 molar Na plus and 1 mole or 1 molar F minus, right? Okay, remember, atoms are conserved. Mass is conserved. Moles and molecules are not conserved because molecules can split, right? Doesn't add any weight for them to split or join together, but now my things present count is going to be different, right? It's like saying, how many things do I have present? I have 1 pen. How many things do I have present? I have 2 things. I have a pen and a cap. I didn't add any mass, right? But my things count, my number of things present is going to be different. Okay, so how much F minus will be present because this NaF has dissolved completely? 1 molar. So I need to take that into account initially. That's initially present because I have dissolved this NaF in there. Okay, so now what will be my change? Well, HF is still a weak acid, right? It's going to dissociate. My Q, if I calculate Q, 0 times 1 divided by 1, my Q is still equal to 0, right? So my Q still needs to get bigger. I'm still going to shift this way. So I don't know how much it's going to shift because it's a weak acid. Let's find out how much it's going to shift. So 1 minus X, X, and 1 plus X. Okay, so I have equilibrium positions for the HF when it's by itself in a solution. I have equilibrium positions for that HF when it's in solution with my salt. So now I need to figure out what my X's are. And to do that, I need a Ka. I need the Ka of HF. It's not on this slide. Let's go find it. Here we go. 6.6 times 10 to the negative 4. Okay. Okay, so another good place to pause. Go calculate your X's and come back with an answer. All right, so my Ka here is going to be x squared over 1 minus x. I'm going to ignore any x's that are added or subtracted, and then I'm going to solve for my x. Okay, let me erase this side so that I have some room to work. And I'll do the same thing over here. All right, so this side is going to be Ka equal to x from the hydrogen, 1 plus x from the F minus, 1 minus x from the HF. Again, I'm going to ignore any x's that are added or subtracted, and I get this. So I already know my K from one side, 6.6 times 10 to the negative 4th. Let's see what the K is on the other side. Okay, so I have my Ka times 1 square root. So my x over here is going to be equal to 0.0257-ish. All right, my pH here is going to be 1.59. Let's see what my pH is on the other side. pH here is 3.18. Whoa, big difference, right? That's a big difference. Okay, so conceptually, let's pause here for a second and think about what happened. So which one's going to be more acidic? HF by itself. HF by itself is going to be more acidic, which means that the hydrogen concentration is larger on HF by itself. Hydrofluoric acid, my initial thing that I started with, dissociated more when it was by itself. Okay, why did that happen? Well, let's look over here. Remember Le Chatelier's principle? If you have a stressor present, your equilibrium is going to shift away from that stressor. Well, it's basically what we did. We introduced a stressor. We introduced F minus, right? And because F minus was present, our equilibrium didn't shift quite as much to that side. Less of our hydrogen, we ended with less of our hydrogen, right? Less of our HF dissociated, resulting in less of our hydrogen ion, which gave us a higher pH. So this is the common ion effect. It's the common ion effect. When there's a common ion present, it's going to suppress the dissociation because of Le Chatelier's principle. Same idea. So once we know this idea, we really don't have to go through all this math in order to decide which one's going to be more acidic. If this was a multiple choice question, now that we have kind of talked through this concept and we've proven it to ourselves mathematically, now we can look at this concept and say, oh, in number 2, there's a common ion present. That common ion is going to suppress the dissociation. Less hydrogen means higher pH. right? So that would kind of be like the logic flow through this concentration. Now, why are we talking about common ions now? Well, for one thing, it's an application of acids and bases, right? So we've dealt with acids, we've dealt with bases. Well, here's a new scenario now, a new context that now we can deal with acids and bases. There is a second reason, though, and the second reason is because we're about to talk about buffers, and buffers are based on this idea of a common ion being present. So you have to understand this math and this concept of the common ion before you can apply it and look at it in this context of buffers, which is exactly what we're going to do next. Okay, so this will be the first practice problem we do when we get back together. All right, and this is an important note about common ion problems. Common ion problems are just normal acid in water problems or base in water problems. They're the exact same problem that we've been dealing with for the whole last chapter, right? The only difference is now there's an initial presence of the conjugate ion. So whatever the conjugate ion is for that acid or for that base, that's going to be present from a different source, usually from a salt. Okay, so that's the only difference between this problem and what we've been doing in the past. Okay, so this brings us to buffers. So you may have heard about buffers before, especially if you've done any work in the field of biology. Buffers are really important solutions. Can you tell me why buffers are really important solutions? You'll find buffers in a lot of different places. You'll find buffers in lakes and streams, in blood, in other animal systems. And basically, what a buffered solution does is it resists a change in pH. So that's really important for something like human's blood. For example, human's blood is buffered at a very specific pH. It's close to neutral, but it's not exactly neutral. But humans are not very hardy beings, right? We can't resist spikes in temperature. If we get too hot or too cold, we will perish. Same thing is true for pH. We really can't resist, we can't survive very large changes in pH. And I'm talking about like a pH change of 1. We would not survive a pH change of 1 in our blood. We would perish. And so our blood is buffered. Our blood does something really cool where it can actually absorb acids. It can also absorb bases without really changing pH very much. It'll result in really minuscule changes in pH, but we can survive minuscule changes in pH. We just can't survive spikes. So this is what buffered solutions do. They resist a change in pH. Now we're going to talk about why. Why can some solutions resist a change in pH when H plus or OH minus is added? Oh, I guess there's a blank for this. There we go. That looks nice. Okay, so chemically, we want to talk about why this happens. How are these solutions able to do this? So the first thing you have to know about buffered solution is that it is composed of a weak acid and a salt. Now, it can't just be any salt. It has to be a salt that contains the conjugate base. Or vice versa. It can be a base and along with a salt that contains its conjugate acid. So both things are present. The weak acid and its conjugate base are present, or the weak base and its conjugate base is present. Now they have to match. If they don't match, it's not a buffered solution. For example, if I can have a weak acid and an anion that is a base, and this is not a buffered solution because this anion that is a base, oh yes, is not the conjugate of my acid, right? It has to be an acid and its very own conjugate base. And you'll see why in a little bit. They have to be conjugates. Okay, so let's look at why this occurs. Okay, so for example, we have a buffered solution and it contains 0.5 molar acetic acid. Here's its Ka, and 0.5 molar sodium acetate. Calculate the pH of this solution. Okay, so in order to calculate pH, remember I care about my hydrogen ion concentration. So no matter what reaction I have, it has to contain a hydrogen ion because that's the thing I care about. So let's pause and do our step one. What's actually present, right? We have acetic acid, HC2H3O2. Now it's a weak acid, so the thing that's going to be most present will be the actual molecule, not the ions, right? We also have a soluble salt. So the thing that's going to be present will be the ions, not the ionic compound. Don't you love having this so much knowledge about chemistry? You can just look at compounds and tell me what's going to be present in a solution. I feel like that should give us brownie points for life. Just the fact that we can do that. That's pretty cool. Okay, so now looking at what our major species are going to be, let's think about the reaction that's going to happen, right? So I have an acid, I have two ions that are a salt. Now, what's the reaction that's going to happen? Keeping in mind, I want to end with a concentration of hydrogen, right? I have a weak acid. I have a useless base. And then I have a weak base. Okay, so my useless base isn't going to react with nobody. It's just going to sit there and watch the show happen. So really, my other two things are going to affect my pH. I need to include those in my reaction. So my reaction is going to be HC2H3O2, and you can write the dissociation reaction, C2H3O2 minus, or you can write the reaction with water. It doesn't matter which one you write because water does not affect the K equation. You can use either reaction. Okay. Now I'm going to take into consideration what's there and see if I can get myself to some equilibrium position. So I start with 0.5 of acetic acid. I start with 0.5 of sodium acetate because 0.5 moles per liter of sodium acetate. If I convert that into moles, oh good heavens, sodium acetate into moles of acetate, what is the ratio of sodium acetate to acetate in this compound? It's a 1:1. So if it dissociates completely, I will have the same amount of moles of sodium acetate. And remember, it's per liter. We're talking about molarity here. So that liters just gets carried over. Okay, do you have to do that calculation? No, but you should pause and consider when this ionic compound falls apart. Will I get the same amount of my ions or will I get a different amount of my ions? Because if this was magnesium acetate, for example, it would not be a 1:1. You would not have 0.5 molar acetate present. You'd have a 1 molar. So pause long enough to make that consideration before you fill in your ice chart. Okay, now will it go forward or backwards? It will go forward because my Q is 0, so I need more products. What will my change be? I don't know because it's a weak acid. So we're going to use an x, 0.5 minus x, 0.5 plus x. Okay, now I have my equilibrium positions. I can plug into my K equation. I'll switch colors to figure out what that x is, because remember, I care about pH. I'm trying to find the hydrogen concentration, right? Oh, if I'm writing the reaction with water, that should be H3O plus. Minor details. Okay, so my Ka, which I have been given for my acid, is going to be equal to x times 0.5 plus x over 0.5 minus x. Now I can assume x is going to be small, and so I end up with this equation because I'm ignoring any of the x's that are added or subtracted. Equals x. Since my concentration of weak acid and conjugate base are the same, these things are going to reduce out of the equation, and my x is going to equal to Ka. Now, pause and mathematically think that's not always going to happen, right? The only scenario in which that's going to happen is when they're equal. If they're not equal, then they're not going to reduce out. Okay, so I have my x now, and I can calculate my pH. So I'm going to take the negative log of my Ka, and my pH is going to equal 4.74. Okay, so I have just calculated the pH of a buffered solution, which looks exactly the same as calculating a pH for a common ion solution, right? Now, we really haven't gotten to the magic of buffers yet. Remember, we said the buffer was special because it could resist a change in pH. So we're not actually going to see the magic of a buffer until we add acid in here and then we recalculate the pH. Or we add a strong base in here and look at what happens to the pH. So that's really what we need to do next in order to see how a buffered solution works. But this slide is good for us to see what kind of things are present in a buffer, what the reaction would look like if I care about the pH of a buffer. Remember that reaction will look differently if I care about ions not included in that reaction. For example, if I care about the sodium ion, I couldn't use that reaction, right? I'd have to use a different reaction. Okay, but I care about the H plus ion. So you have seen what an ice chart looks like. It looks identical to what a common ion effect ice chart would look like, which looks identical to all the ice charts from chapter 14, with the exception that I have an initial quantity of my conjugate base present initially, right? And then you can see how we plug in and solve for pH, which looks very similar to the common ion effect and calculating pH in chapter 14. So we really haven't done anything revolutionary yet, but that's going to come next. Okay, on the next slide, what we're going to do is we're going to take some base and add it to the solution and see what happens, right? See if the buffer actually does resist a change in pH and what that looks like. Okay, now before we move on to that slide, take a minute and note what is your pH here? 4.74, right? Because we're going to want that to compare once we add the base into the system. Okay, let's do it. So calculate the change in pH that occurs when 0.01 mole of solid sodium hydroxide is added to 1 liter of the buffered solution described in the previous example. Compare this to the pH change that happens when 0.01 mole of solid sodium hydroxide is added to 1 mole of water. 1 liter of water is what that should say. Okay, so we're going to do a calculation twice. We're going to do adding solid sodium hydroxide to water and adding solid sodium hydroxide to a buffer. So let's do the easier one first. We're going to add sodium hydroxide to water. Now, you can calculate the change in pH that happens with this one. This is an easy one for us to do, right? We know that the pH of water is going to start at 7. What's the pH of the solution going to be when we add 0.01 moles into 1 liter? Okay, now before you go crazy on this, I just want to show you that they're giving us amounts in moles and liters. Remember, our ice chart and our K equation must be in molarity. So I would suggest that you convert things right away into molarity, because if you get rolling on this problem, it's really easy to forget to do it at the end. Okay, so notice that I've done it right away. And 0.01 molar divided by 1 liter is just 0.01, but it's worth stopping ourselves and thinking through that process. Okay, good time to pause it. Finish this problem. Tell me what the pH is at the end. Okay, so this is a strong base. I know it's going to react completely. It's not going to hit. So I know what the change is, right? I don't have to mess with the X's because it's not a weak thing. So I can take my hydroxide concentration. I can plug that into negative log. I can get the pOH, which is going to be 2. So that means the pH is going to be 14 minus 2, which is 12. Okay, so if I put 0.01 moles of solid sodium hydroxide into 1 liter of water by itself, my water changes from a pH of 7 to a pH of 12. That's a pretty big jump in pH. All right, let's look at what happens when we do this in our buffer. Okay, so remember our buffer had 0.5 HC2H3O2 and 0.5 C2H3O2 minus. Okay, so now we have a third thing present that is going to affect pH. It's the OH minus, right? 0.01, and that's in molarity. Okay, so I need to rethink my equation, because that original equation that I had where it was just acetic acid dissociating, this is the equation I was using on the other slide. Okay, that doesn't have hydroxide in there anyway. So now I need to rethink my reaction and rewrite a reaction that involves hydroxide. This would be a good time to pause here and see if you can do that. So what's hydroxide going to react with? The acid, right? Bases react with acids. So I'm going to set up a reaction where my acid is reacting with my base. And when that happens, I'm going to form water, H2O, and I'll have acetate left over. Remember, the water is going to be pulled, or the hydrogen ion is going to be pulled off by the hydroxide. So 0.5 molar, 0.01 molarity, which we already calculated, 0.5 molar. Again, I get to ignore anything that's a liquid or a solid because it doesn't affect my K equation. Now, what's the change going to be? I have a weak acid and a strong base. Is it going to be equilibrium because this reaction is driven forward by my weak acid? Or is it going to be to completion because this reaction is driven forward by my strong base? So the thing that's stronger is going to drive it. My strong base is going to drive this to completion. Negative 0.01, negative 0.01, positive 0.01. Okay, so what are my equilibrium positions? 0.49, 0.51. Okay, so I have this hydroxide has pushed and pushed and pushed and pushed and pushed until something is gone. Either the hydroxide's going to be gone or the acid's going to be gone. In this case, it's the hydroxide. The hydroxide runs out first. So I am left with my weak acid and my conjugate base once again. Now notice I'm not left with any hydroxide or hydrogen ion. So I'm going to label this ICF because we're not necessarily at equilibrium. We don't know. We're not at equilibrium unless all of our ions get plugged into the K equation and my Q is equal to my K. So is this the case? Well, I don't know. Let's set up a reaction that's going to work with my K equation. So I'm going to reset up that reaction. C2H3O2, that's dissociating into H plus and C2H3O2 minus. So now I have 0.49, 0.51, and 0. Okay, I have 0 H plus. So is my Q equal to Ka? No, it's not, which means I need to run this again to equilibrium. So ICE. What's my change? I don't know. I only have weak things present. 0.49 minus x, 0.51 plus x. Okay, so now we're in a familiar place. Let me move myself over so I can plug this in to the K equation. So I'm going to get my Ka, which I know from the slide before is equal to my hydrogen ion, my acetate ion, my acetic acid ion. Okay, again, I can assume X is going to be really small. I can ignore anything that is added, any X that is added or subtracted, because it's probably not going to add significantly to my numbers. Okay, and now I am in a place where I can solve for X. So the Ka was 1.8 times 10 to the negative 5. Okay, so now, oops. My numerator and denominator, the numbers there don't cancel, so I have to deal with them. So times 0.49 divided by 0.51, I get an X that is equal to 1.7 times 10 to the negative 5. Okay, remember X is my hydrogen concentration, so I can take my negative log of that, and the pH is 4.76. Well, dang, look at that. So when sodium hydroxide was added to pure water, the pH changed by like a pH of 5. When sodium hydroxide was added to my buffer, the pH changed went from 4.74 to 4.76. So it only changed by 0.02. Same amount of base caused a pH change of 5 versus a pH change of 0.02. That's a big deal. It's a big difference. So let's take a minute, just pause and try and figure out why this happened. Right? So what happened with my buffer that didn't happen with my base by itself? Okay, so notice that when my base was by itself, and it dissociated, all of it became hydroxide, right? Well, when that happened with my acetic acid and acetate ion, what actually occurred was not a buildup of hydroxide ion, right? Which is what happened in water. Hydroxide ion just built up. What happened in my buffer was that the hot hydroxide ion reacted, and my weak acid reacted to form my weak base. So with water, I just built up hydroxide, built up the super strong basic ion. With my buffer solution, I got a buildup of a weak base, right? And that led to a small change in pH versus a big change in pH. So that's what we're talking about. This buffer is able to absorb base and become a weak base. It's able to absorb acid and become a weak acid, right? Instead of accumulating these very strong ions, it's able to shift and build up weak ions instead, which don't change the pH as much as the strong ions do. Okay, one other thing I want to touch base on before we get off of this problem was how we dealt with the numbers. Notice that we kind of dealt with this in a two-step problem, right? Step one, when we added the base to a buffer, was reacting until something was gone, right? We reacted to completion. It's like we swung the pendulum all the way over, and then we went to equilibrium. So the pendulum swung back. Notice that step two is going to equilibrium. So we separate these two things. Chemically, they probably aren't separated like this, but mathematically, we separate them so that it's easier to deal with, right? We go all the way to completion. The strong species is going to drive us until something is gone. Once that something is gone, it's either going to be a strong acid or base that's left, or it's going to be weak stuff and we swing back to equilibrium. So when you deal with this problem, it's much easier to separate it into these two steps. Okay, so that's a lot for today. Let's pause there. Think about this, try some practice problems out of the book, and then when we come back together, we'll try some of these practice problems together. Okay, let me know what questions you have. I will see you in class.